Okay, so here we are, friends. We've reached stoichiometry, which is kind of the um, narrative climax of a year one chemistry course. Is kind of the central piece of what you're doing when you do chemistry. And this first video is going to kind of be an introduction, precursor to actually diving into stoichiometry, where we're going to talk about interpreting chemical equations. What is stoichiometry? Stoichiometry is using chemical equations to solve for chemical quantities. So this is kind of bringing together all of the pieces that we've learned so far, balancing chemical equations, understanding reaction types so that you can build those chemical equations and then using them to solve for chemical quantities, specifically our mole calculations. But before we get to that, what we're going to look at is we're going to look at how to interpret chemical equations, and some of this is a bit of a review. So here I have a reaction statement for you. It says complete the reaction in which a solution of barium hydroxide reacts with phosphoric acid. So let's start with a skeleton equation. So go ahead and pause the video and see if you can write out the chemical formulas involved in this particular reaction. Okay, so here's the skeleton equation that hopefully you sorted out. We start with barium hydroxide. Barium ion is a 2 plus ion. Hydroxide is a polyatomic ion, OH1 minus. So you're going to need 2 hydroxides for each barium. Phosphoric acid, you'll remember I ate it and it was icky. So we're looking at that phosphate ion, which is PO4 3 minus. So you're going to need 3 hydrogens. This is, of course, a double replacement reaction. We have 2 compounds going to 2 compounds. Specifically, this is the type of double replacement reaction that we refer to as an acid-base neutralization. Barium hydroxide acts as our base, and phosphoric acid, of course, acts as our acid. And those produce a neutral compound, water. In addition to that, they produce the salt barium phosphate, which you can see the formula there, and balancing the charges means this 3 bariums, 2 plus each, and 2 phosphates, each at 3 minus. Go ahead, if you haven't already done so, and balance the equation. Get the right coefficients. Again, take a second, pause the video if you haven't already done that. So here we have our balanced chemical equation. Your coefficients are 3, 2, 1, 6. Let's talk about the different ways in which you can interpret those equations. One is to think about it as a series of interacting particles. So here we're talking about 3 formula units of barium hydroxide reacting with 2 molecules of phosphoric acid to produce 1 formula unit of barium phosphate and 6 molecules of water. This represents the lowest ratio of particles that are involved in this reaction. And if you have less than 3 barium hydroxides, if you have less than 2 phosphoric acid molecules, you cannot, this reaction cannot proceed. This is the bare minimum number of particles. Also notice that we start with 3 formula units on one side, but we only have 1 formula unit on the other side. So in a chemical reaction, we can rearrange the way things are combined. But we can also scale this up. And we can talk about it in terms of large numbers of particles. And there we take those coefficients and we look at them instead of interacting particles as in interacting quantities of moles. So 3 moles of barium hydroxide react with 2 moles of phosphoric acid to produce 1 mole of barium phosphide and 6 moles of water. If you're doing lab bench chemistry, when you are actually performing labs in which you will need to do stoichiometric calculations, you are most likely working on this mole basis. And then notice here, because it's groupings, we can have portions or fractions of the reaction. So if you only have, for instance, 1 mole of phosphoric acid, then it would take 1.5 moles of barium hydroxide to react. With that, half a mole of barium phosphate would be produced. And of course, you can have half a mole because it doesn't require you to break any of the particles down. The same way I can have a half dozen eggs without having to break any eggs apart in order to take it from 12 eggs to 6 eggs. All right, so those are the 2 ways to interpret the coefficients, but there's also a bunch of other things embedded in chemical reactions. So here's the same reaction again. And what I would like for each of you to do now is pause the video and see if you can find the molar mass for each of these 4 substances. Just be good practice in calculating molar masses. So again, pause the video. Don't worry about the coefficients, just find the molar mass of each of the compounds. So here are the molar masses, and you can kind of check your work there. Again, if you're within one or two of the last digit, it either means you're using a different periodic table or you have a rounding issue, so you might go back and check. Now, what I want you to do is determine the total mass of reactants and the total mass of products. So what you're going to need to do there is you're going to need to multiply each of the barium hydroxide, or the molar mass of barium hydroxide, sorry, by 3, phosphoric acid by 2, and so on. So here would be an equation for calculating total mass of reactants and total mass of products. Go ahead again, pause the video, do the math real quick, and see what you get. You shouldn't be surprised to find out, of course, that the total mass of reactants and total mass of products is the same. And this is largely due to a fundamental feature of chemistry, and that is the law of conservation of mass, that the total mass of a closed system remains constant. Mass can neither be created nor destroyed. You have to have the same number and types of atoms before and after a chemical reaction, so it would stand to reason you would have the same mass. You're just rearranging the way things are connected. Here's a pie graph, because pie graphs are funny. One of the other things we can look at are gas phase reactions. So we can look at interactions of volumes of gases at standard temperature and pressure. And you may remember the relationship between volume and moles is that 1 mole of any gas at standard temperature and pressure is equal to 22.4 liters. So here's another chemical reaction described. You should go ahead, pause the video, and write a balanced chemical equation. So here's the skeleton equation. We've got fluorine gas. Remember, it's diatomic, so you need 2 of them. We have ammonia gas, NH3. We've seen that molecule before. Dinitrogen tetrafluoride and hydrogen fluoride, which, if you recognize that as an acid, we could also name that hydrofluoric acid. If you go ahead and balance the chemical equation, again, if you haven't done so, pause the video first. But your coefficients there should be 5, 2, 1, and 6. And so if we were to take the 5 moles of fluorine, if we're looking at those coefficients as mole coefficients, multiply it by 22.4 liters, what we find is that we have 112 liters of fluorine gas reacting with 44.8 liters of ammonia gas to produce 22.4 liters of dinitrogen tetrafluoride and 134 liters of hydrogen fluoride. And if you add up the total volumes of reactants and products, much like the mass here, we get the same volumes, at least close to the same. Remember, the last digit's an estimated digit. So is it the case that volume is conserved in a chemical reaction? Well, let's look at one more equation. And again, you should take some time to try and balance this equation. I've already written it out for you in the skeleton equation anyway, so you should pause the video and balance it. Okay, so 4, 5, 4, 6 is your balance for this equation. And what we see if we look at the moles of gas on each side is that we start with 9 moles and we end with 10 moles. And again, it shouldn't be surprising that we can do this because you're rearranging the way things are grouped. And so when we group things in different ways, we can get different total numbers of groups and our outcomes, either more or fewer. And so you multiply each of those again by 22.4 liters, and of course it shows us that you do not always have to have the same volumes of gas. And this can be put to use if, for instance, you're wanting to use a chemical process to inflate an object. You start with a substance that has a small number of moles of gas, even start with reactants that are all solids or liquids. And then if the reaction produces a gas, then that gas could be put to some particular use. So you might want to go ahead and make 2 columns now. What we're looking at is what things are conserved and what things are not conserved in a chemical equation. So you should make the 2 columns and look at those quantities in the center and see if you can figure out which side they belong on. So again, maybe pause the video so that you can make some predictions about where you think each of these things should go. Okay, so if we look at representative particles, as our first one, representative particles are not conserved. And again, we've already seen this in our first chemical reaction. We looked at starting with a certain number of formula units, but not having the same number of formula units in the products. Sometimes formula units can produce molecules or vice versa, so representative particles can change both in types and quantities. Moles are also not conserved. Again, we just saw this in a previous equation. Because you're grouping things in a different way, you might end up with a different number of moles. Mass, on the other hand, because of the law of conservation of mass, has to be conserved. Volume, which is dependent on your number of moles, should not surprise many of you that that is not necessarily conserved in a chemical reaction. But atoms, the main reason we balance chemical equation is to make sure that we're conserving the numbers and types of atoms on both sides of a chemical equation. So that is kind of the precursor in interpreting chemical reactions, and specifically we're interested in those mole coefficients in a balanced chemical equation, and we'll use those in the next video to begin our discussion of stoichiometric calculations.